Hello, welcome to a video on scatterplots, correlation, regression, and regression lines. In this video we're going to learn to make scatterplots from a table of data, interpret information given in a scatterplot, compute these correlation coefficients, or what we call the R value. We use R to represent the correlation coefficient, write an equation of regression line, and use sample correlation coefficient to determine whether there is a correlation in a population. Alright, so the first things first, a scatter plot. What is that? It's a collection of data points. And when we say data points, we mean an XY pair. So there are actually two things being measured here, whatever the X variable is and the Y variable. So it can be any person or an object, and every person or object that's in our sample or our data set, we're making two measurements on them, and we're going to plot both of them. Alright, and we use a scatter plot to determine whether two quantities seem to have some type of a relationship. Alright, correlation is a measure to determine if there is a relationship between the two. So what it means is a clear relationship between the two quantities, and we use correlation, the idea of correlation, to determine if there is a relationship between two variables and the strength and the direction. Alright, and you'll understand what we mean by direction hopefully in this next slide. So this scatter plot, this over here in the X variable, when we're plotting those points, is our years of education, and then here vertically we've got a score on a test that measures prejudice, right? Someone's prejudice. And what we're seeing here is there seems to be this trend that the higher we go to the right, which is more and more and more and more years of education, the lower this level of these test scores on a test measuring prejudice. So the further we go to the right, we seem to be going down, right? And if we had like a trend line in here, it's like pointing in the downward direction as we move left to right. Alright, so what the trend that we see here is that people with increased education, that's the X variable, tend to have a lower score on the test measuring prejudice. Right? And that's what the scatter plot is revealing. Now, correlation and causation, two completely different ideas. So although we just saw something that looks to show us what we call a negative correlation, meaning one's going up, the other's going down. We'll get into that later. But just because we see a strong correlation doesn't necessarily mean that we can say that the education causes a person's level of prejudice. Okay? So, well, what could be causing it if it's not the increase in education? Well, it could just be happening by chance. It could just be a coincidence. But then, more than likely, it's got to do with these other two things. Education involves classrooms, and the classrooms we typically are around a group of diversified people, different kinds of people. And just being around different people, or being exposed to diversity in a classroom, could be a root cause, because we are not isolated like people who don't go to school for long. You know, the people down here, they didn't go to school for long, so they weren't able to be around different people enough to know that they're not any really different than they are. Okay, and then it could be that the education that they received requires them to think about things differently, and those different insights in the different ways, the education caused the person to be more tolerant and less prejudiced. So that could be the education is really what's the root cause there, but it could be just the exposure, being in school that long and being around other people. So we don't know, and it's probably a combination of the two. But correlation shows a link, but it does not show causation. Okay, you cannot measure causation via correlation is the big important thing here. Alright, a regression line. A regression line is the line that best fits our scatter plot. Okay, it fits it better. It's of all the lines that could go through the data, the regression line is the line that goes through it the best. Alright, sometimes you'll hear me refer to it as the line of best fit, or the regression line. Alright, correlation coefficients. The correlation coefficient that we use in this course and that we use in most statistic courses is R, and it measures the strength of the relationship between the two variables that we're measuring, like before the education and the score on that test. The correlation coefficient would measure that, and it would be a very strong correlation, but it would be a negative number because it was one went up and the other went down. Right, positively correlated means if one goes up, the other goes up. If one goes down, the other goes down. And then negatively correlated, like the one we just saw. One goes up, the other goes down, and vice versa. Alright, if there's perfect correlation, positive or negatively, it means not only does the regression line, the line of best fit, describe the relationship of the trend well, all the data points hit the line perfectly, or the line goes through all the data points perfectly. It like passes right through the center. So instead of what we saw, let me give you an example. So here, a line does a really good job here, but it's not going to hit every data point perfectly because it's just, you know, they don't fall perfectly on a line. Some of them just happen to miss. But if you had perfect correlation, like we were describing down here, perfect correlation, every single data point that you had, so if you had, you know, however many data points, they would fall perfectly in a line. And then your best fit line would just go right through the center of every single one of them and just split it right in half, right down the middle. Right, there wouldn't be any stray data points with perfect correlation. You would have everything fall perfectly on the regression line. So here is a kind of a flow of regression lines and the correlation coefficient for those different scatter plots. So we're starting off with the highest measure of correlation that we can have. 1, R equals 1. That's the highest that we could possibly have, and that's when a positive sloping line, remember a positive slope means it increases left to right. It goes up left to right. If a positive sloping line passes through every data point right through the center, then that's perfect correlation, and R will be equal to 1. Okay, but what's more likely is that a line does a really good job going through the data, but not every data point hits it perfectly, like we miss with some data points. Right, and most of the time, even when you have very strong correlation, like an R value of 0.8, which the closer to 1 you get, it's really strong. But that's just, it's more likely to miss than for the line to go through any one of them directly at all. It's just we're close to the line when we have strong positive correlation and strong negative correlation. But as we see, as we make our way from R equals 1 down to R equals 0.3 and then 0, you see that tight linear pattern just breaks apart. And then over here, when we're at R equals 0, which is the worst measure of correlation, there just doesn't seem to be any rhyme or reason to where points are going to show up. And what I mean by that is sometimes when we have a low, let's remember this is X and this is Y, when we have a low X value, sometimes we have a low Y value. Sometimes when we have a low X value, we have a high Y value. And then sometimes when we have a high X value, we have a low X value and a low Y value and a high Y value. There's just no rhyme or reason to where these points are going to show up. It's like buckshot. So when R equals 0, when the correlation coefficient is 0, that it insinuates that there is no correlation between these two variables. They may not have anything at all to do with each other, whatever these two things are. So you could have something like the price of a new TV set, and then the amount of snow in Alaska. They're just not going to have anything to do with one another. It could just be all over the place. But if you have something like the amount of snow in Alaska, and if you had something like down here, let's do the negative one, like distance from the equator, distance from the equator on X, and temperature for Y. That's gonna have a nice linear pattern. The further we get from the equator, the lower the temperature typically goes. Alright, and so this is a little interactive thing, and I wanted you to see this is going to show R, and it's going to show the equation of the best fit line. And I'm just going to add points. So when I add 2 points, no matter where I put my points, R is going to be 1 when you only have 2 points, because only one line will fit through 2 points. But watch, when I make a third point, if it doesn't fit on the line perfectly, we still have a pretty strong R value, meaning close to 1. Okay? But remember, what R measures is how well a line fits through the data. So I could put a point, as long as I'm close to this line of best fit, R is going to stay close to 1. But if I pick a point way off of the line, notice R starts to drop down pretty drastically. And I haven't picked anything up here, but this would, like, way up here would be way off the line. So if I picked a point up here, again, our value starts to get really close to 0. So I'm going to pick these points until eventually I have an R very, very close to 0. Now, I'm also going to put some points in space that are in a linear pattern. And then what I can do, and then notice R is strengthening when I start putting points that are in a linear pattern. Now I'm almost up to halfway. I'm going to click this X, and I'm going to click these points that are way far off the line. And you'll see that R get really, really strong fast when we start eliminating these points that are not really close to the line. The closer all the points in the data set are to a line, is what makes R big and close to 1. Alright, and then the same thing, if I made it go downhill and be really close to that line, I get a strong R, but this time it's close to -1. So the negative sign on R determines it kind of goes along with the slope of the line. This is a negative sloping line because it's going down left to right. And the one we saw earlier was a positive sloping line because it was moving up left to right. But R is kind of a measure of how close the points are to the line. If the points start leaving the line, leaving the linear pattern, then you start to see R decrease in absolute value towards 0. And that means there's not any rhyme or reason to the pattern of our data. Alright, now here's something that's going to scare you to death. Here's the formula for R. Yikes. That's a scary looking formula. Okay? It's not bad in Excel, and we'll look at it in Excel. But just know that you will get some Excel shortcuts for this, and don't have to worry about doing this by hand. Okay? Use Excel. Okay, and I'm going to show you how to do it. I'm going to show you how to use this formula, and it's fine if you use it. I'm going to show you how to use the formula because if you click on View an Example in your homework, it's going to assume you're going to use that formula. But I'm going to show you how to use Excel to get that thing in 1/10 of the time. Alright, but in that formula, remember all that summation notation. When we see the sigma, remember sigma means sum, so every time we see sigma, we see sum. Okay? And just make sure that you know the difference between these last ones down here. When we have no parentheses, order of operations takes over, okay? What comes first, adding or exponents? Exponents. So this is the sum after we square. So this is the sum of the squares. And then right here, it's still order of operations, but parentheses is always the top dog. So this time the sum comes first, and then we square. So this is the square of the sum. So just make sure you understand the difference between these two, because they do mean two completely different things. Parentheses are important. If they're not there and then they are there, that typically does change things. Not always, but it does typically, and usually they're there for a reason. And in this case, they definitely are. Alright, so we're going to do it real quick. We're going to go through the process of doing this. So this is back to that years of education, the score on the prejudice test. So the person who had the most education had the lowest score on the prejudice test, meaning they scored low on it. And then this is the person with the least amount of education. They scored high, and then so did this one. So that's where the numbers are coming from. If we went into our table, these are x's on the top row, so they would go in this first column for x. And then the y that corresponds to them, notice they have to be paired up. So 12, 1, 5, 7. 12, 1, 5, 7. Okay, these are pairs. They have to be paired up when we're doing scatter plots. Alright, and then notice this is these two rows, columns multiplied together. 12 times 1 is 12. 5 times 7 is 35. Again, if you're thinking Excel, you should be thinking, oh, this is just going to be equals this thing click times this thing click. And I'll get that and drag it down. Okay, this is x squared. Oh, that's equals click this and then square. Shift 6 squared. And click and drag down. So this is, again, it's a table format. It looks like something you would type up in Excel anyway. Alright, and then down at the bottom, this is the sum of the x's, the sum of the y's, sum of x times y, sum of x squared, sum of y squared. And then we would literally just take that and plug it into that thing. Okay, it's ugly, but that's how we would do it. Alright, and then plugging it in, that would give me this thing right here, and then going to a calculator or something, simplifying, I would get that negative 0.92. Alright, now let me show you how easy this is in Excel. Alright, so I got my data in. I'm going to highlight all this data from here down to here. Okay, and I will let me just blow it up so I can actually see. So once I've highlighted, I'm going to insert a scatter plot. Alright, there's my data. I'm going to right click on any of these points here, and I'm going to click add trend line. And then over here to the side, I'm going to tell it linear because I want a trend line, and then display equation and display r squared on the chart. Alright, and then there is r squared, and then all you have to do then is take the square root of that r squared. Okay, so this is 0.84. I'm going to do second square root 0.8492. Alright, and I get the 0.92 roughly, and because it's downhill, it's a negative, and I know that that's what we got right here, negative 0.92. The square root is going to give me the positive square root because it's the square root function, but that is it's a squared value. So you can square a negative and get a positive, you can square a positive and get a positive. So this is always positive, but if you take the square root, it could have been positive or it could have been negative. The sign comes from this sign of the slope of the regression line. If that's negative, then it's a negative r when you take the square root. If it were positive, then you would take a positive r and it would have been a positive slope. Okay, so that's one way to get it. Another way to get it, probably even easier. So in this cell down here, I'm going to type in equals, and I typed in CORR, and notice it pops up COREL, returns the correlation coefficient between two data sets. So double click that, and then it says, tell me your x's. So I click and highlight. Alright, and then it wants a comma, and then it wants the y's, so I highlight those, and then enter, and there's the correlation coefficient. All right, so that's 100 times easier, but it also, the other way also gives you the trend line. It also gives you the equation of the trend line, which we're going to do in just a second in the notes. But if you're just after R, if you're just after the correlation coefficient, then that's going to be your easiest method. The CORREL. Highlight your X's, comma, highlight your Y's, and then enter. And that's Excel's really fast, easy way to do all that crazy formula right there. Alright, the regression line equation. So this is the line that we just saw Excel give us in the last thing, the actual one I clicked on that box. It said show the regression line. That's what this is. So the M comes from, there's all that summation notation that we saw before. And then the B, again, sum of the Y's minus M, all of this, times the sum of the X's divided by the N. So once again, there's a crazy formula for this regression line that goes through the data that we were using Excel for just a little bit ago. But Excel can find it for you as well. So once again, my strong advice to you is to use Excel for this as well. Alright, and Google Sheets does the same thing as Excel does. So if you don't have Excel, you have access to Google Sheets. Alright, so with that same equation that we did, there's the computation. We found all these values back earlier. So all of them are part of this formula here, and it's the same exact things that we found before. So we just plug them in, and there's the M and the B. Okay, we already did this when we did Excel just a little bit ago. So notice this equation of the regression line that we're getting here in the notes. Y equals negative 0.69x plus 11.05. This was the regression line Excel gave us. Negative 0.6868x plus 11.011. And it's just rounding. And maybe that have a data point in there wrong. But anyway, Excel can do this regression line equation for you very quickly and easily, and much more time efficient. Alright, I'm going to make another video with just using Excel for these types of problems, finding R squared, finding the regression line, and doing it quickly and efficiently. I'll also show you how to use the table to do this, but it's easy to just use those little shortcut formulas in Excel for this.